Section 7.1, Basic Trig Identities. Going to start with a couple of vocabulary terms here. The first one is identity. An identity is simply an equation that is true for all values of the variable. Now, in Algebra 1 and Algebra 2, we would solve equations, and once in a while, we would get an answer of all real numbers. And that would happen when you get something like 3 equals 3, or 0 equals 0, something, not 0 equals 3, 0 equals 0. And that would be an example of an identity. All real numbers means any number you pick would give you a true statement. And the same thing can happen with trig, and it's going to happen a lot with trig, and we're going to be using these identities a lot in Chapter 7. So a trig identity is simply an identity involving trig functions. Now this video is going to be mostly just explaining these trig identities, laying them out for you. We're not going to do a whole lot with them in Section 7.1. We are going to use them quite a bit in Section 7.2. We're going to use them to prove and verify specific statements. The first set of identities is the reciprocal identities, and we kind of know what these are already. This just kind of formalizes it. So the reciprocal identities look like this. So the sine of theta, we know that when we're talking reciprocal, we're flipping fractions over. So if we flip the sine over, what we get is the cosine. So the cosecant. So the sine of theta is equal to 1 over the cosecant of theta, and that's the first reciprocal identity. There are 6 of these reciprocal identities. So the sine of theta is equal to 1 over the cosecant. The cosine of theta is equal to 1 over the secant. And the tangent of theta is equal to 1 over the cotangent of theta. Now the kind of the ones that the companion ones, we'll call them companions, we can write them the other way around. The cosecant of theta is equal to 1 over the sine of theta. The secant of theta is equal to 1 over the cosine of theta. And the cotangent of theta is equal to 1 over the tangent of theta. Okay, so those are the first identities, the reciprocal identities, and we kind of used these already in the past when we talked back in Chapter 5 about finding the sine, cosine, tangent, cosecant, secant, and cotangent, the 6 trig values of a given angle. We're just kind of formalizing these into identities. The next group of identities are the quotient identities, and there are 2 of these. And we kind of talked about these in the past too, maybe not necessarily in a video, but in class they probably come up. The tangent of theta is equal to, now if we think about the unit circle, we said that the tangent of any angle was equal to the y value over the x value in on the unit circle. And if you remember from the unit circle, the y value is the sine of our angle, and the x value is the cosine of our angle. So the tangent of any angle is equal to the sine of that angle over the cosine of that angle. The second quotient identity deals with cotangent, and this we can kind of think about the reciprocal identity with cotangent. Tangent and cotangent are reciprocals of each other, so it makes sense then that the cotangent of theta is equal to the cosine of theta over the sine of theta. The next set of identities are the Pythagorean identities. The textbook gives you 3 of them, but I'm going to expand on them a little bit, and this is actually going to be 9 different identities. Okay, so the first identity that the textbook gives for the Pythagorean group is this. It says the sine squared of theta plus the cosine squared of theta is equal to 1. Now, when you see sine squared of theta, what that really means is the sine of theta squared. Okay, so it's just a simple way to write something, the square of a trig value without using parentheses. So if we needed to square the sine of theta minus 1 or theta minus pi or whatever, it's just easier to write it this way so we don't have so many sets of parentheses. Just a little side note there. So this is the first identity the book gives us. Sine squared plus cosine squared equals 1. I'm going to expand this and say there's 2 more identities that we could define based on this statement. We could say that the sine squared of theta is equal to 1 minus the cosine squared of theta. Or what we could say is that the cosine squared of theta is equal to 1 minus the sine squared of theta. And we'll use these identities quite often. It's a matter of manipulating one part of the equation for another. All of these are true statements. All of these are valued or are equivalent. They're all identities. They all work for any angle. So we may need to use a variation of this, meaning this or this, to do what it is we need to do. And that'll be more into Section 7.2. The second Pythagorean identity that the textbook gives says the tangent squared of theta plus 1 is equal to the secant squared of theta. And let me redraw that exponent of 2. There you go. So the secant squared of theta. Now, again, building off this, solving for one of these two variables or getting one of these parts by itself, we could say that the tangent squared of theta is equal to the secant squared of theta minus 1. Or we could say that the secant squared of theta minus the tangent squared of theta is equal to 1. Again, we may need to use specific orderings here to do what we need to do. And like I said, that'll be section 7.2 when we start verifying identities. The last Pythagorean identity the book gives us is 1 plus the cotangent squared of theta is equal to the cosecant squared of theta. And then building off of that, we could say the cotangent squared of theta is equal to the cosecant squared of theta minus 1. Or we could say that the cosecant squared of theta minus the cotangent squared of theta is equal to 1. Okay, so we really have 9 identities. The book only gives you the 3 in red if you were to look back in the book and find those, but we can get 9 out of those when it only gives us 3. The last set of identities in section 7.1 are the opposite angle identities, and there are 2 of them. The first one states that the sine of negative a, so if our angle was a negative angle, let's say negative 30, okay, that's equal to, whoops, I'll go back to the pen, that's equal to the negative sine of the positive version of the angle. So if this was the sine of negative 30, that's equal to the negative sine of positive 30. Or the second one says the cosine of a negative angle, whoops, let's try that again. Negative angle is equal to the positive, or the cosine of the positive angle. So if this was the cosine of negative 30, it's equal to the cosine of positive 30. So those are all of the identities in section 7.1, the basic ones. Now let's actually use these identities to accomplish some tasks. The first set of examples says use the given information to find the trigonometric value. So the first one is going to say something like this. If the secant of theta is equal to 3 over 2, we need to find the cosine of theta. This one's pretty easy because we know that secant and cosine are reciprocals. We don't necessarily need to go back and look and use this reciprocal identity where we go 1, so it would be this one here. The secant is this, so we go 1 over the cosine. We know that they're reciprocals. Okay, so to find the cosine of our angle, all we need to do is flip this fraction over. We could say the cosine of theta is equal to 2 over 3. Okay, that one's a pretty easy one. Let's ratchet it up just a little bit here. Number 2, if the cosecant, CSC, if the cosecant of theta is equal to 4 over 3, what I want you to do is find the tangent of theta. Now, if you look back at your identities, what you're going to find is that none of the identities directly relate cosecant and tangent. So I'm going to just make a little note. So no identities relate cosecant and tangent. So what we're going to have to do is we're going to have to use multiple identities, use more than one to find the tangent of our angle, identities. Okay, if you do look back, and if I'm thinking more this Pythagorean theorem, specifically this one right here. This is the one right here. Sorry about that, a little pause there. I'm thinking of this one because we have cosecant and cotangent, and if I could get the cotangent, then all I would need to do is flip it over, and that would give me the tangent, because cotangent and tangent are reciprocals. So let's give this a shot. We know the cosecant is 4/3, so I'm going to look back to this identity. 1 plus the cotangent squared is equal to the cosecant squared. Now, just as a matter of shorthand, and because I'm lazy, I'm going to refrain from writing the theta every single time. Okay, it just seems repetitive and unnecessary, because we know we're going to be taking the cosecant of an angle, which it's not just going to be cosecant of nothing. It's always going to be an angle. So I'm not going to worry about writing the angle every time. And it just helps save us some writing and helps save us some time. So the Pythagorean identity that we're going to use, like I said, is this one here. So we're going to have 1 plus the cotangent squared is equal to the cosecant. Whoops, let me go back to that. CSC squared. So 1 plus the cotangent squared is equal to the cosecant squared. So let's fill in what we know, because we know the cosecant. We know, obviously, 1 is a value. It's not going to change. So the only thing we don't know then is the cotangent. So let's fill in again what we know. So 1 plus, we don't know the cotangent, so that's cotangent squared, is equal to the cosecant squared. We know the cosecant is 4/3 squared. Okay, so let's fill things in. Let's simplify a little bit. So 1 plus cotangent squared is equal to 4/3 squared, means 4/3 times 4/3, so that's 16/9. And then we need to get cotangent squared by itself. So I'm going to need to subtract 1 from both sides. So that would be like, this would be 9/9. So 16/9 minus 9/9 gives us 7/9. So the cotangent squared is equal to 7/9, which then, to find the cotangent itself, we would need to take the square root of both sides. So the cotangent is equal to the square root of 7 over the square root of 9, which is 3. Okay, so we've got the cotangent. Now, how do we relate that back to the tangent? The tangent is the reciprocal of the cotangent. So we need to just flip over our fraction here. So the tangent is equal to the reciprocal of this, so 3 over the square root of 7. And remember, we don't want square roots in the bottom of our fraction, so we're going to need to take this times the square root of 7 over the square root of 7. So 3 times the square root of 7 is just 3 square root of 7, and square root of 7 times the square root of 7 is the square root of 49, which the square root of 49 is a nice number. That would be 7. So the tangent of theta, if you want to write your theta in, you can. Tangent of theta is equal to 3 square root of 7 over 7. And since we were solving with square roots, we do need plus or minus, because either one is possible. It doesn't tell us where the angle is, so we can't say definitively whether it's a positive tangent or a negative tangent. Before we get into the last set of examples, I want to just go back and do just a little bit of recall, the plus, plus, minus, minus rule, and what it's used for. So if I make my table here one more time, 1, 2, 3, 4, so this is going to be sine, this is cosine, this will be tangent, and I'm going to have quadrant 1 and 2 and 3 and 4, so Q1, Q2, Q3, Q4. Remember, plus, plus, minus, minus, plus, minus, minus, plus, and plus, minus, plus, minus. So what this is used for, it tells us the sign, meaning SIGN, of each trig value depending on which quadrant it is in. And that's going to help us do this last part here, where we have to express each value as a trig function of an angle in quadrant 1. So this also kind of goes, this will touch briefly on the opposite angle identities, but I would say it's easier to use the plus, plus, minus, minus rule rather than the opposite angle identities to find this. So you express each value as a trig function of an angle in quadrant 1. So number 1 here, what I want you to find is the sine of 600 degrees. Now, we can do this in our calculator, but that's not really what it's asking. It's asking us to write it as, our answer is going to be something along the lines of sine of some angle, and this is going to be, I guess I can write it in the parentheses, this will be a quadrant 1 angle. That's what it really is after, and we might need a plus or minus out front. We'll see. Before we can decide if we need that, if we need this minus sign, so I'll just erase all this for now, is we need to figure out the reference angle, and that's really what we need to do first. So let's find the reference angle, because remember, reference angles are always listed or in terms of quadrant 1. So the reference angle, we're going to need to, first of all, we're bigger than 360, so we have multiple rotations, so we're going to need to get this down between 0 and 360. So we're going to take 600, and we're going to subtract 360, and that leaves us with 240, and that's between 0 and 360. So this was just one time around plus a little more. 240 degrees is in quadrant 3. Okay, it's between 180 and 270. So then to find its reference angle, we're going to take 240 minus 180, and that's going to give us 60 degrees. Okay, so what are we going to do that? So we can say that the sine of 600 is equal to the sine of 60. Now the question is this going to be positive or is it going to be negative? So we're talking sine, and we are in quadrant 3. So sine quadrant 3, that's a negative. So the sine of 600 would be equal to the negative sine of 60. That's how we're going to use the plus plus minus minus rule here, is figure out what angle or what quadrant it is in, find the reference angle, and then use the plus plus minus minus rule to figure out if this is going to be a positive or a negative. Let's try another one here. Number 2. We're looking for the sine again of 19 pi over 4. So now we're talking radians, but the rule is still the same. Find the reference angle and then go from there. Okay, so 19 pi over 4, we need to find the reference angle first. Since we're talking in pi over 4s, 2 pi radians, again, goes all the way around the circle. 2 pi over 1 becomes 8 pi over 4. So what I'm going to do is I'm going to subtract 8 pi over 4, because remember, this is 2 pi, and 2 pi is 1 full revolution, just like 360 is 1 full revolution. So we're just going to subtract multiples of 8 pi until we're below or between 0 and 8 pi over 4. So let's just keep going here. So 19 pi over 4 minus 8 pi over 4 is still going to be over 4. Remember, when you add and subtract fractions, the denominator never changes. 19 minus 8 is 11, so 11 pi over 4. But that's still bigger than 8 pi over 4, or it would still be bigger than 360 if we were talking in terms of degrees. So we're going to need to go one more time. So minus 8 pi over 4. This leaves me with 3 pi over 4, and that is definitely in that first revolution around the unit circle. 3 pi over 4, if you don't have the unit circle, take a look at it, but this would be 135 degrees in terms of degree measures, but 3 pi over 4 is in quadrant 2 this time. Okay, so how we're going to write this answer, we can say the sine of 19 pi over 4 is equal to the sine of 3 pi over 4. Now, quadrant 2 sine, let's go back up and look. Quadrant 2 sine is right there. It's positive. So this is our final answer right here. Sine of 19 pi over 4 is the same as sine of 3 pi over 4. And I just realized that I made a mistake. 3 pi over 4 is not a quadrant 1 angle. So what we need to do is we need to actually figure out the reference angle. Silly me. So I'm going to just cross this off because that's not our answer. We'll just ignore that and just cross that off, scratch it out, erase it, whatever you need to do. So we need to figure out the reference angle. So 3 pi over 4 is a quadrant 2 angle. And if it's in quadrant 2, remember we take the negative x-axis, in this case, is pi. So 1 pi minus 3/4 pi is 1/4 pi, so pi over 4. That's a quadrant 1 angle. So now we can write our answer. We can say, and I'll do this in green, we can say the sine of 19 pi over 4 is equal to the, and again, we're still quadrant 2, so it's still going to be positive sine of pi over 4. Man, I was so excited that we got something in between 0 and 2 pi that I forgot to find the actual reference angle, pi over 4. So sine of 19 pi over 4 is equal to the sine of pi over 4, which is also equal to the sine of 3 pi over 4. Let's try a couple more here. And I'm out of space on this page, so I'm just going to turn the page here. So number 3, we have, let's see, cosine this time. Cosine of negative 410 degrees. All right. So cosine of negative 410 degrees. Obviously, this is not between 0 and 360, so we need to get it between 0 and 360. We're not going to subtract 360 this time. We're going to add because we are negative. So we're going to go negative 410 is equal, let's see, don't want to do equals. I want to go plus 360. And negative 410 plus 360 is negative 50. And it's still not between 0 and 360, so we need to add 360 more, and that will give us 310 degrees. That's between 0 and 360. 310 is in quadrant 4. So we need to find the reference angle. I'm not done yet. So I'm going to take 360. Since it's in quadrant 4, we're going to take 360 minus our angle, 310, and we're going to find that that's 50 degrees. And that should make sense. We were at negative 50, which is also in quadrant 4. We could have thought of it that way. 360 minus 310 is 50 degrees. So the cosine of negative 410 degrees is equal to cosine of 50 degrees. That's our reference angle. So I'm going to flip back. So quadrant, or 410, negative 410 degrees was in quadrant 4, and we're looking at cosine. So if I flip back to my table here, cosine in quadrant 4 is right there. It is a positive cosine. So when we look back here, cosine of negative 410 is equal to the cosine of 50, and we were done. If we had anything else to add, the only thing would be a negative out in front, but we don't have to since the cosine in quadrant 4 is positive.